Welcome to the Massachusetts Alternative Septic System Test Center, or MASS-TC. Today I'm here with George Hoyfelter, and we're here to discuss a very exciting project funded through 319, which is non-point source pollution. George, what are we here to talk about today?
We're here to talk about phosphorus today, or P. P is an essential element in our universe, and as life evolved on this planet, nature incorporated into all our tissue, all our living tissue, and now it becomes sort of an essential element for us. So the thing we're here to talk about today is not only its importance, but how we manage it and how it becomes problematic when we mismanage it.
What are some sources of phosphorus in the natural world?
Well, phosphorus is mined from rocks, from minerals. So there are various places in the world where we have large mines pulling it out so that we can use it to fertilize our food. And then that gets incorporated into our tissues. So it's like vitally important. All our DNA, our RNA, DNA, our muscles, our tissue, everything that allows us to do what we're doing now, to talk, relies on phosphorus and energy cycling processes in our body, from ATP to our DNA to anything else we use in our body.
So you say phosphorus is mined. Is that mined for agricultural purposes, or?
Well, the primary reason right now is for agriculture, for supplying the world with food. So the major use of phosphorus today, why it's mined, is like 90% of it is used for food. There are some used in detergents, although since the 70s that's been waning because of the damage that it's done in our wastewater going out into particularly freshwater environments where it produces pretty noxious effects.
So if phosphorus is a natural element that we need, why would it be an issue?
Well, it's like any other contaminant, and the story is many-fold, where we take an element that's essential or one that's incidental, we concentrate it, we put it in one spot, and nature, which has really no value judgment on what we do with it, will take it and incorporate it into something that sometimes we don't like. And in this case, the most obvious one is cyanobacteria blooms. In fresh water, when phosphorus enters into fresh water, the algae or the cyanobacteria take it up and they use it. And in their body pathways, in their cell pathways, they produce toxins, which are hepatotoxins or neurotoxins. And when we breathe them in or drink them incidentally during our recreational use of water, or we use it as a water source, that can damage our liver and have neural damage. So that's primarily worldwide is the largest negative impact of phosphorus on freshwater environments.
And on Cape Cod, there are sometimes signage that goes up, especially over the summer, that indicates there are some algae blooms. Is that right?
Yes, that's exactly why they post them, is when the cell counts, when the bacteria or the algae counts get so high, that's related to the possibility that these neurotoxins are also very high and could damage anyone who incidentally ingests them. Particularly, for instance, pets, which go down to the water and drink the water. If the cyanobacteria concentrate on one side of the pond because of the wind, and they windrow up and the dog drinks, or the cat, or any other animal, or a man, or we're playing around, or little kids in the shallow water, ingest it, then that's when the impacts are felt. Also, it's been known that people just water skiing in ponds or lakes that have algae blooms where it aerosols up and they breathe it in have difficulties. So the health effects are many and varied, and they also vary with the species of blue-green algae that grow in the ponds. But on Cape Cod, we've seen an increasing number of those over the years, probably partially due to more surveillance and partially due to warming temperatures and increased phosphorus loads from septic systems.
How have health agents or health officials dealt with phosphorus in ponds in the past, or what's one way they might have treated it?
Well, the go-to right now for ponds is to use alum, or it's an aluminum compound which binds the phosphorus, and then it settles to the bottom, and then it's out of the biological cycle. So it's no longer available to the blue-green algae or the cyanobacterium, and therefore they don't bloom, and they don't produce a noxious effect. So that's been the go-to, but it's sort of an end treatment. It's like, putting a Band-Aid, unless you're stopping the blood coming out of other parts, which are all the influence to the pond. You end up having to treat this all the time with alum, or after so many years with alum. And really, it's not the optimal way to treat it, because you're also taking the phosphorus out of the cycle. And I think the goal for anything would be to get phosphorus to the point where once we use it, we can get it back into use again as a fertilizer or something else, rather than giving it a one-way trip.
So on Cape Cod, as you said, increased land use and development is increasing the phosphorus load into our ponds. As far as that ties into wastewater, does it not?
Absolutely, because wastewater is one of the main inputs. It's the most obvious one. There are other ones, stormwater, there's atmospheric deposition, and even a minute part that comes from marine ocean sprays. The phosphorus gets lifted up during, storm events and things like that, so it brings the phosphorus inside. But the largest source by far would be our wastewater, and that which we put onto our lawns and gardens if it has a direct pathway into the ponds.
Let's talk more about wastewater. How do large-scale treatment plants deal with phosphorus?
Well, there's a number of technologies that have come about to treat it in large wastewater treatment plants. And I'll say in general, just before we go into that these processes I'm about to talk about are having trouble being, there's a big challenge bringing them down to the on-site level, but that's what our project is all about. So let's talk about the large treatment plants. There's a number of ways that they have treated for phosphorus. One is to bioaccumulate it. Just like the blue-green algae take up the phosphorus, they encourage organisms that bioaccumulate or take more phosphorus than they'll ever need into their body mass, and then settle those out and pump them out before they can be discharged with the wastewater from the treatment plant. That's one way. It's rather hard to manipulate that, but there's more and more science to be able to direct that sort of operation. There's polymers which bind phosphorus, usually with a metal complex like iron or aluminum, and they bind it before as it's passing through the wastewater stream so it doesn't go out with their discharge. But then they have to deal with that polymer and the discharge, the sludge that comes with that polymer. There are other means. Most of them are either precipitation. There's some polymers that are exchangeable, so they could reuse them or regenerate them, taking the phosphorus out. But there's a lot of research needs to be done for large-scale recovery of phosphorus from large treatment plants. They have a little problem. Those processes, when you think about on-site systems and the variability at a house, you have some real challenges manipulating those processes.
So let's talk about nitrogen and phosphorus, because both can be limiting nutrients, and we certainly hear a lot about nitrogen on Cape Cod.
Yes, nitrogen pollution is also an issue, and the nice thing, if there is any nice thing about nitrogen, is that it has a gaseous cycle. So that means that we incorporate it into our tissue, we discharge it in our wastewater, but by manipulating the biology, we can get that back up into nitrogen gas. I'm not saying it's not a challenge, because it's obviously a big challenge, a challenge on Cape Cod, and we need to do it. But the technology is a little bit easier to manipulate, because the final product is a gas, and gases just go away. And if they're not noxious and kill people, they're fine. And we're breathing 4/5 of nitrogen. It's what makes our sky blue. Who doesn't like blue skies? So nitrogen is an issue, particularly in the marine environment where nitrogen is limiting. In other words, that's the thing that stops the growth. But in freshwater, phosphorus is limiting. So if we add phosphorus, the bugs that there, the bacteria, cyanobacteria, they say, okay, I got plenty of phosphorus. Where do I get nitrogen? They just get it from the atmosphere, because 4/5 of what we're breathing is nitrogen. So they have an unlimited supply of nitrogen, but no phosphorus. So we start the fire with the phosphorus. And that's a little bit more difficult. There is no gaseous phase of phosgene, unless, of course, you're a terrorist making phosgene gas. And I don't think that's happening. So that is like a solid, the gift that keeps on giving. Because once it gets into an environment, it cycles, just like it would in the atmosphere with nitrogen. But it cycles through that part of the cycle which we don't like, which is the cyanobacteria. So what we have to do is physically remove the phosphorus, either for reuse or get rid of it altogether, like the alum that they add to ponds really seals it in the pond forever. Well, forever until somebody goes through and dredges it up. So that's the challenge with phosphorus. The challenge is, here's something, we give it a one-way trip to, say, a freshwater environment, and we can't get it out unless we harvest it or unless we do something else with it, like they do with alum.
So it sounds like with wastewater, it's kind of an uphill battle when it comes to removing nutrients. Absolutely.
If you look at sort of the difficulty in removing contaminants, at the bottom rung, the first thing you can get rid of is biochemical oxygen demand and the suspended solids, which are kind of ugly to begin with. And they're easy to get rid of. Just blow air into it and settle it. There's no magic there. It's science. It's not rocket science. As you come up, you get into the bacteria and viruses. Those are a little bit easier to handle because we have known disinfection techniques. And even in the Onsite setting, soils do quite a good job if you give them enough time and enough spread out. Then the next step up is nitrogen, which has a cycle. And if you can manipulate that cycle biologically, which is fairly easy because it does itself without us watching it, we just have to give it the right environment. And then the next step up would be phosphorus. And that's the difficult one because there's no gaseous cycle. And then above that, of course, we have contaminants of emerging concern, which we're all dealing with today. Again, an instance where we've rearranged things and put them in the wrong place so that they kill people.
And now a standard Title V septic system is only going to get that first step, the secondary treatment?
Yes, pretty much right below the system, 6 to 12 inches down, it does the first part. It does a little bit of the nitrogen removal also, and does a little bit of the pathogens, particularly bacteria removal. And the phosphorus removal is totally dependent on the soils there. Is going to be, is there something to adhere to? Is there something that will attract the phosphorus and bind it? Or in some instances, do you keep the wastewater up high enough so that it goes through the biogeological cycle to actually get incorporated into plants? And then we harvest the plants. Either we cut the lawn and move the stuff away from the environment we don't want it in, or we grow crops with it, or things like that. So there are different techniques.
So for this grant, we're going to be exploring a lot of these on-site innovative alternative technologies that exist for wastewater. So we have some incentives for folks to install one of these new types of technologies that report to remove phosphorus, which includes a $5,000 subsidy for a number of homeowners to install the technology like this, as well as donations of equipment in many cases, depending on the technology for homeowners. So it's really an exciting opportunity, is it not?
Yeah, we were very fortunate to be able to participate in this. And what we've done really is to pull together all the different types of technologies that I'm glad you used the word purport to remove phosphorus, because we don't know whether they do yet or not. There's none of them with any general use approval in Massachusetts. There's some with some piloting. And they really go on a number of different principles, some of which are scaled down from treatment plants, and some which are, they're just guesses as to whether they'll work.
So we talked about wastewater treatment plants and how they've dealt with it. How about on-site systems? How can technology be used to remove phosphorus?
Well, as the technologies have evolved, there's sort of broad classes that we could talk about as far as the new technologies on the market and those sort of strategies employed. There's electrochemical, there's sort of the binding agents using some sort of resin or binder for the phosphorus. Then there's the natural soils-based systems. And a little outside of that is the pilot approved in Massachusetts, the PhosRid, which stands for reactive iron dissolution.
All right. Let's talk about electrochemical.
Okay, electrochemical, there are two main electrochemical ones that are on the market now. One has pilot approval in Massachusetts, that being the iron-based system that Waterloo has, ECP. So basically what they do is to run current through a metal. In one instance it's iron, and the other it's aluminum. And that frees up the iron or the metal ions, which bind with phosphate and then either chemically bind and precipitate out in the leach field, or they chemically bind and settle in the tank in the case of aluminum. Iron moves out into the leach field, and in the case of aluminum, it settles down in the sludge, which is pumped and brought to a treatment plant. So you hyperaccumulate it there and get rid of it so it doesn't go into that waste stream.
Can such a system be retrofit or put in where a homeowner maybe has some components already?
Yeah, that's the nice part about it, because you can actually put it in a pump chamber or sometimes in a septic tank, and it will work. You just, eventually those metal plates are going to get used up because you're actually creating from the solid. You're going from zero valence up into dissolving the plates so that they'll get used up. And that will depend on the amount of water that you're feeding it. And many of these systems have sensors to indicate when they should run the current through the plates in order to free the ions and bind with the phosphorus based on temperature or sometimes flow rate.
So that way the electricity through the plates is not always running?
It's not always running, and you're not always wasting, so to speak, the ions. They're just going out and not binding with anything because there's no phosphate coming in.
Are there increased electricity costs for such a system?
Yeah, many of these work on like millivolts, so I don't think you'd probably see the cost of those in a normal operation. If they went haywire or something, maybe, but for the most part, they're only going to come on with very small voltage and current during the operation and what they're doing, and then they shut off when they're not.
Might there be an increased charge as far as having to pump more frequently?
Yeah, with the aluminum, of course you would, and we need to know how much aluminum gets concentrated in that sludge to be able to take it to a treatment plant. And with the iron, probably not, because all of those dissolved components, although you get some of them settling out in the tank, most of those are going to the leach field and forming compounds like strangite, vivianite, some of the ites that you see. And phosphorus chemistry is one of the most complex chemistries I've ever had to deal with. And almost any metal forms in many of the valences of the iron. So I can't even keep track of all the ites that are out there.
So if for the Waterloo ECP there are these phosphorus-bound chemicals that are forming in the leach field, won't eventually that clog up the leach field? Yes,
eventually it will, but well beyond the life frame of a normal leach field, which is, say, 20 to 30 years. These would, if you did the math or the stoichiometry, figuring out how much phosphorus to how much iron, where it would go and how big it is, would be over 100 years before you clog a leach field in normal sand. You might have to think about it if you had tight soils, but for the normal sands down here that they're applied to, and the ones that represent the biggest problem with phosphorus transport, you'd be well over 100 years before it would bind that. And we tested it here at MassTech for quite a while and actually looked at some of the compounds, and we have some electromicrographs that are available, and maybe we'll be able to show them, that show the compounds binding and how small they are relative to the sand grains.
In such a system, because it uses these iron plates, those have a lifespan as well?
Yeah, those will have a lifespan of anywhere from 2 to really 4 years, depending on how much they are used. I mean, a seasonal home, you might go for 5 years. A year-round home, probably every 2 years, I think, is what they suggest.
And there is a donation of this equipment?
Yes, particularly Waterloo Biofilter is donating up to 3 systems that can be given away. And then the homeowner gets a subsidy, as you mentioned. And then the engineering costs are fairly minimal, above and beyond a standard Title V, since they're really just sticking plates into a component and putting a control panel somewhere to monitor it.
So let's talk about some of the alternative technologies.
Oh, other than the electrochemical, there's other ways to bind phosphorus. And some of these are out there in technologies such as FujiClean and I think phosphorate. They don't presently have approvals in the Commonwealth, but they are sort of a scale down of creating some sort of polymer, which is sort of embedded, metals are embedded in there that bind the phosphorus. And then occasionally you'll have to replace them because there's only so many binding sites in a sheet or an element that you place in the way of the wastewater as it's going by. And you'll have to sort of pull those out and replace those. Now, there's no electricity involved. That's somewhat of a physiochemical process, and it's not a real tight chemical bonding. So that offers the ability to possibly use or replenish the plates or the media by some process by which you can desorb the phosphorus and then reuse that. But, we haven't got a whole lot of experience with those, and I haven't seen a whole lot of data even in the published literature about them.
The phosphorate, as far as considerations for a retrofit or existing components, is there anything folks should know about that?
Yeah, I don't believe that you can use primary effluent for that. So you really need a treatment system ahead of that, and that may be so also for the FujiClean, that you have to remove a lot of the BOD and suspended solids beforehand, because many of the resins or many of the sort of attachment media, if you don't have those clean, then the binding sites get tied up with all the organic matter that you have to get rid of in the primary processes. So a lot of those follow treatment trains. And, that, of course, adds to the expense of the system and the complexity of the system.
So FujiClean does actually have provisional use approval currently, but for nitrogen reduction.
Right. This would be a pretty good appeal if they bring in a phosphorus reduction unit to follow it, because they already have some approvals in the Commonwealth. I think the only downside there is we have no idea how or if the technology works. I'm sure as they're developing it or have developed it, they've rolled it out, but we just don't have any data or information on it.
But potentially, if they work, a FujiClean, which has also been donated for this grant project, could potentially provide both nitrogen reduction and phosphorus reduction.
Yeah, that would be an exciting twofer that we could get. So I'm looking forward to at least giving it a shot.
Excellent. Let's talk some more about the phosphorid technology.
Okay, phosphorid is a little bit different in that it uses, phosphorid stands for reactive iron dissolution. And that means that it creates the environment where if you add iron, like plates, but usually a media, like a steel ball or something like that, that it will be so reduced conditions that it frees up the ions or the cations so that the phosphates can bind to it. And then that is sent to sort of a sacrificial leach field type thing, a filter, where it precipitates out, rather large amounts precipitate out. And that filter would have to be changed out because now it's going to be a very phosphorus-rich, phosphorus-bound, chemical-rich environment that, again, we might be able to recover because struvite, for instance, which will form in those conditions, is used as a slow-release fertilizer. So it's possible that that could be used if allowed, because, of course, wastewater passed through it, so we have a little bit of a contamination issue from pathogens and things. But all of those things are things that, to this point, we have not, as a society, been really, chasing down the phosphorus recovery piece. But I believe in the future we're going to need to be.
The Phosrid, it currently has pilot use approval in the state.
Yes, and there are a number of them out on Nantucket, and the results look very promising there. So we will probably, in the longer term, we need to get an idea of what the recovery is as far as changing out the media and what you do with the media afterwards. Since it's fairly new, that being in the last 10 years, we haven't had to face those problems yet, but at some point somebody's going to have to empty one out and figure it out, that sacrificial filter. What do we do with the media now?
And the Phosrid, can it be placed at an existing system in a retrofit?
Well, you probably could retrofit it if all your elevations were correct, because you do need a gravity flow through it, and you do need a chamber. So you've got a couple of chambers to worry about, and there's elevation drop across all the chambers. So I think you'd need to have an engineer answer that question for a particular site.
Let's talk about the soils-based wastewater treatments.
Okay. Well, in soils, it's a little tricky because most soils-based removal is going to be based on or be determined by the amount of sort of metals in the soils that you're feeding it to. So on Cape Cod, we have iron in our sand, so the iron will bind up so many sites. And also the fine texture of sand. Sometimes clays, which are charged particles, will attract the phosphorus and physically bind it for a while. But at that point, when you're relying on just the physical binding, you have to think about how many binding sites do we have, because it's sort of like a juggler. If you give them 2, they can easily do that, and that would be a clay particle. It can easily handle 2. You throw 3 balls in there, and they easily do that. 4, 5. As soon as you get above 4, at some point, those are going to drop. And those balls that are dropping, just think of them as phosphorus passing by that juggler, who is the clay particle that is handling as much phosphorus as it can. It just passes it on to the juggler beneath it. But eventually there'll be a breakthrough. And that can be calculated, and it's based on physical characteristics of the soil. And then the metal characteristics of the soil, the metal oxides in particular, those will determine how much phosphorus can be removed. So it's a little bit chancier in the soils-based system. So to sort of hedge the bet, you want to put the soils-based systems up very shallow, like a drip system or like something we use here, Geomat. Both of those products are approved in the Commonwealth. And in the upper soil layers, the AB layers, which have finer texture and will hold more phosphorus, you can keep it up in the biological recycling. So the roots can get down to the phosphorus and use it, cycle it up to something we kind of like to see. Most people like to see green things up above ground. And then it can be harvested, of course, at that point. But it prevents it from traveling quickly to the groundwater and then in moving in the groundwater toward our ponds where we don't want it. So the soil-based systems are great. They use 2 primary means, actually 3. One is biological recycling. Then you have the physical binding, which is temporary on the fine soil particles. And then there's sort of the chemical binding which might occur when there's metal oxides involved. Not that those chemical bindings are irreversible, but they're less reversible than just the physical attraction of the phosphate to the clay particles. So that's the basis of how they work. They definitely would be called for in instances where you cannot apply a technology which is more advanced and involves bells and whistles. It may be a passive way to remove the phosphorus, but at some point it's going to break through. So there should be some thought in the future, maybe the distant future at some sites, that you would remove that leach field material and actually be able to co-compost it or something and reuse it, because we have to get back into recycling phosphorus. I mean, if you look at some of the figures, and there's a lot of argument around this, but phosphorus is very limited in the Earth's crust as far as being able to get it without concurrently pulling out a lot of heavy metals and things we definitely don't want to be spreading around. So the more we can recover phosphorus, the easiest manner would be the ideal way to do it.
So with the perchlorate and the geomat in these upper soil horizons, is that going to change the size of the leach field?
Yeah, most likely it will, because leach fields are sized based on the percolability of the soils. In our AB layers, the perk rate is slower than in the sandy layer beneath it. The one mistake we've made on Cape Cod, and we continue to make, is to discard those top layers and get down to the sand and let the wastewater fly. If we had just thought about this, even incorporate this into land use, we would accommodate them by larger leach fields in shallower soil horizons. I don't believe we'd be in half the mess we're in right now, because we've seen that those shallow soil horizons deal with nutrients better, they deal with pharmaceuticals, personal care products better, they deal with pathogens better. So really, you get a 3 or 4-4. You get a lot of removal right there, and some of those processes are natural, they're going on, and they've been going on long before man walked on the earth.
And it sounds like if someone were to install this in these upper soils, they may even have a greener lawn for it.
Oh yeah, they will definitely have a greener lawn, and I think you can see from some of the pictures we've shown that you get some green lawn where there's drip systems or these other systems, the other shallow base systems. Doesn't mean you couldn't use a non-proprietary shallow drain field. Some of those are also designed.
And both the perchlorate and the geomat have donated equipment?
Yes, they have, because they are both very anxious to see and to prove with monitoring from third party that they get nutrient removal. In some places are already granted that, for instance in Maryland. But really getting in on how much they remove, that's going to be very important to figure out, because with those soils-based systems, shallow systems, you also have evaporation, evapotranspiration. I mean, the lawn is pulling up that moisture and it's getting rid of the moisture. So you're concentrating. It's very difficult to figure out how to work that into the calculation of true nitrogen removal. And we're doing some projects here at MassTech to actually calculate that.
So let's talk about one of the other ways that you can be a part of this project.
Certainly. The one which I never leave out of anything, whenever I give a talk, is composting toilets. Because we spend 5 minutes in the John every morning, some of us longer, and we're contaminating nice clean water when the obvious question is, why do we contaminate the water in the first place? Why do we use nice clean water? So composting toilets sort of cut out that middleman, that carrier water, and leave it for drinking purposes and other beneficial use. And I believe that composting toilets is a very appropriate manner to passively remove or displace the nutrients from where we don't want them, because you package them up right in the compost itself. And that you can manage by putting where it's not going to do any damage. So the phosphorus removal and the nitrogen removal we found out that you get somewhere around 80% nitrogen removal and even more than that phosphorus removal because it ties it up in the compost. In the way of nitrogen, there's actually some denitrification that takes place. In the phosphorus, it ties it up, and you can definitely recycle that. In the Commonwealth now, you're allowed to actually use a composting toilet, get a 50% reduction in leach field, and you have to bury your compost 6 inches below the ground, which that's debatable whether that's really the best way to do it, but it's, I guess, the safest as far as the pathogens go. But this offers, in large management scheme, you could really manage nutrients in a watershed. The only problem is that it's definitely not reached the tipping point where people will accept it yet.
So who might be an ideal candidate to get a composting toilet?
Ideally, of course, you'd have to understand all of what a composting toilet involves, which is not a whole lot, but these are ideal for situations near ponds and lakes where small pond and lake, they're never going to run a sewer to their technologies, usually electricity, and some have only 60 amp service. So ideally something that could really benefit from a very passive, easy way to remove the black water. And you would remove all the water fixture toilets in your house. You'd still have the gray water, so you still need to dispose of the gray water. But that would take care of all of the phosphorus, nitrogen, pathogens. You got it. I mean, it's all right there.
Great. And it's probably worth mentioning.
Oh, don't worry. This isn't pee. I wasn't trying to mislead you. Well, there is pee, but there's pee in the tea. So phosphorus is in tea also.
So it's probably worth mentioning with most of the technologies that are involved in this grant that homeowners will need to know about the operation and maintenance agreement that goes with innovative alternative technologies.
Yes, as with in all alternative technologies, there's a maintenance contract required in perpetuity for them. And this is just to make sure they work. I mean, people do it for their heaters. I mean, I just got a notice for my heater and an annual thing on those new high-efficiency heaters. They do it for their swimming pools. So, I mean, it just makes sense that you have something controlling your major discharge of wastewater from your house that you would have a maintenance contract so you don't have to delve into it. You, by the way, could do your own maintenance contract if you're a Class 2 or Class 4 treatment plant operator.
So phosphorus is clearly a very complex subject, and this is an exciting opportunity. Where do you see, in an ideal world, what would ultimately phosphorus removal and the cycle look like?
The ideal world would be that we would recycle what we have. And, you know, people make jokes about pea cycling or whatever, but, you know, since urine is a major cause, and it's probably easiest to sort of separate, not exactly the best smelling, but the easiest to separate, then in an ideal world, that would get recycled. You might have urine separating toilets. I could foresee the day when somebody would come and pump your system out, and they would appear at your door with a small check to say, hey, here's the $5 for the phosphorus we just grabbed from your house to offset some of your costs, or who knows? I mean, because if we do go into phosphorus shortage like was predicted to happen in nitrogen before we could have a process to make it, then, you know, food shortages and things like that are in our future if we don't do something. And I think our busy lives are going to come to a grinding halt if we don't at some point turn around and say, you know, why are we wasting water? In my ideal world, you look in the dictionary under W and you cannot find the word wastewater because there is no wastewater.
That's strong words to live by. Waste no water.
Yeah, waste no water.
Great. So it sounds like this is really an amazing opportunity and one that we're hoping people will really jump into.
It really is. And speaking of jump into, if they do engage in it, they'll be able to jump into their pond without worrying about cyanobacteria bloom, because that's going to be in our future if we don't do something about it. And just to put this in perspective as a closing, there's a lot of ways that you, the homeowner, can deal with phosphorus. Like, you live near a pond, you don't need to see that lawn sweeping down right to the water. You don't need to compost right at the edge of the water because you're adding the phosphorus. You don't have to clear the vegetation all the way down to the water like I see every time I go out on a kayak ride. These people with beautiful lawns down to the water, and then they wonder after they fertilize, how come the water is turning green on me? How come I can't swim in it? So I think that it's an exciting opportunity to deal with the wastewater component, which can be pretty hefty or pretty high percentage in some locations, but also an opportunity to become aware of phosphorus in our daily lives, what it means to us, because when it's not there, life comes to a grinding halt.
Well, thank you so much, George. We really appreciate you talking to us.
Glad to do it. And sorry about the misunderstanding with the P. And, I always say there's P and T and there's TP. Well, what else?
My name is Emily Michelle Olmsted, and if you have more questions, we certainly are going to plan to put out some more informational sessions just like this and even dive deeper into the technologies. But you are welcome to contact me, and here is my contact information. Thank you.